capacitor. Capacitors I see. So what is capacitor and what is the relevance of capacitor? All we have discussed in our basic classes, right? Basic electrical class. Once more, I will be telling you about that. In our basic electrical class, we have discussed about capacitors, right? What is the relevance of capacitor? So we have discussed about reactive power and active power there, right? Reactive power and active power. So active power is a power which is actually consumed by an AC circuit, inductive load. Reactive power is a power that is used for making the magnetic flux inside an inductive load. Then inside a building, most of the loads will be inductive type. So more reactive power will be required by the inductive load. So when the reactive power increases, electrical efficiency will be decreasing. Then losses will be increasing. Conductor size will be increased. Voltage drop will be happening. System efficiency decreases. Energy bill will be increasing, right? By improving the power factor or by compensating the reactive power, let us overcome all these disadvantages and they become advantages like reduced losses, reduced conductor size, improved voltage regulation, increased system efficiency, less energy bill. You know, we cannot reduce the reactive power, we can only compensate that. For compensating the reactive power, thus by improving this, for improving the power factor, we are using capacitor or capacitor banks. Actually, we are having different methods for power factor improvement: static capacitor, synchronous condenser, phase advancer. Out of them, most probably or generally we are using static capacitor or capacitor bank. Okay. Then this capacitor can be used in various methods or various types. Suppose I am having only one inductive load in my building. Okay. So there, suppose I am having an induction motor, only one type of inductive load, that's an induction motor. There I can connect a capacitor in parallel with that induction motor. This is called as individual compensation. Individual compensation. Okay, individual compensation. Then suppose I am having a group of inductive loads. For example, I am having a group of induction motors which are controlled from an MCC. There, for controlling that group of inductive loads, I need a group of capacitors. That is called as group compensation. So you can use there a capacitor bank. Group compensation. Okay. Then suppose inside my building, I am having plenty of inductive loads. Different types of inductive loads are there. So all of them, its reactive power, I need to compensate or I need to maintain the power factor always centrally. So there I use a central compensation method. Central compensation method. An APFC or a capacitor panel can be used. So individual compensation for controlling or compensating only one inductive loads reactive power. Then group compensation is for compensating the reactive power of a group of inductive loads. Central compensation. Central compensation is used centrally. For a building is having different types of inductive loads. So for that electrical system, its reactive power has to be compensated centrally. All its reactive power has to be compensated centrally. Then there you should use central compensation method. Okay, then when you are using a group compensation method or a central compensation method, you can use two types of capacitor banks. First one is fixed type of capacitor bank. Second one is APFC, that is automatic type of capacitor banks. Okay, so if you are using a capacitor bank, two types can be used: fixed type of capacitor bank and automatic type of capacitor bank. Okay, suppose fixed type capacitor bank. So where we are using this fixed type of capacitor bank, if the reactive power rating of the capacitor bank that we are calculating is less than or equal to 15% of transformer rating, then we need a fixed type of capacitor bank only. Okay, and what is the specialty of fixed type capacitor bank? It supplies constant amount of reactive power. So if reactive power or kVAR of capacitor bank that we are calculating is less than or equal to 15% of transformer rating. Okay, so already we know about the transformer rating, right? So if the capacitor rating kVAR value is less than or equal to 15% of transformer rating, there we need a fixed type of capacitor bank only. But if we are having that value which is above 15%, kVAR of capacitor bank is above 15% of the transformer rating, there we should use automatic type of capacitor bank. Okay, so what is the specialty of automatic type of capacitor bank? Its reactive power is adjusted as per the loads. That is, when we need only less amount of reactive power, it's that capacitors which is producing less amount of reactive power, that only will be operated. But for a fixed type of capacitor bank, we cannot automatically adjust that. So always, suppose for example, if you are having a 100 kVAR of fixed type of capacitor bank, always it will be giving you an output of 100 kVAR reactive power. But sometimes we don't need this much reactive power. Sometimes we need like less amount of reactive power, then we cannot control that automatically. Always this will be the output of the capacitor bank in case of fixed type of capacitor banks. But if you are using an automatic type of capacitor bank, based on our required reactive power load, we can adjust it. Automatically it is adjusted. That is automatic type of capacitor bank. Okay, so APFC panel means automatic power factor correction panel. APFC panel. APFC panel means automatic power factor correction panel. So power factor is an indication of reactive power, right? Because we know power factor is equal to active power by apparent power, which is the resultant of active power plus reactive power. So as Q increases, power factor will be decreasing. So for improving the power factor, you know, power factor is just an indicator. Real thing is reactive power. So for inductive loads, reactive power will be more. More reactive power will be required for magnetic flux, right? So as the reactive power increases, power factor, that indicator will be reducing. So we will be checking the power factor from a meter, right? So that will be shown as low. If the reactive power inside a system is more, then the power factor is shown as less. When we are compensating for this reactive power, power factor will be increasing and it is improved now. It's a good power factor, optimum power factor now. For the optimum efficiency of an electrical system, always the power factor should be greater than or equal to 0.9. Okay. Okay, so that is APFC panel, automatic power factor correction panel. Okay. So I'll be telling you about the different components which are used inside the APFC panel. Before that, let us go back to the capacitor selection. Okay, now you know what is the relevance of capacitor sizing, right? Okay. So capacitor selection, how to select the capacitor or how to size the capacitor. For sizing the capacitor, we need to calculate how much reactive power is actually required by that electrical system. Normally, you know what is the unit of a capacitor? Unit of capacitance is farads, right? But when you are seeing a capacitor in an electrical system, it will be rated in kVAR. For example, if you are seeing a capacitor in an electrical system with 10 kVAR of rating, that means this capacitor is able to compensate 10 kVAR of reactive power. Okay, so that is capacitor. Okay. So we need to calculate how much reactive power we need to compensate first. For calculating that, we are having an equation, load in kilowatt into tan phi 1 minus tan phi 2. So what is this tan phi 1 and tan phi 2? See, phi 1 and phi 2 phase angles. Okay, tan phi 1 minus tan phi 2. So actually, how can we find out this tan phi 1 and tan phi 2 for our calculation? Load in kilowatt always will be known. We need to find out tan phi 1 and tan phi 2. Okay, suppose I am having an electrical system whose power factor, current power factor is 0.6, for example. Okay, and I need to improve this power factor to 0.9 or 0.95. So actually cos phi 1 power factor, it is cos phi. So cos phi 1 is 0.6. So you can find out phi 1 by taking the cos inverse of 0.6. Okay, after taking the phi 1, you will be getting tan phi 1. Then power factor 2. This is my initial power factor or the current power factor. This is my final power factor or the target power factor. So that is cos phi 2, 0.95. So cos inverse of 0.95. How much it is? Like we need to calculate that, right? So we will be getting phi 1 and phi 2 from cos inverse of 0.6 and 0.94. Okay. So from there, we will be getting this tan phi 1 and tan phi 2. After getting phi 1 and phi 2, then now we can calculate tan phi 1 and tan phi 2. Okay. So using that, we need to calculate the required reactive power that we need to compensate. Kilowatt, load in kilowatt into tan phi 1 or active power into tan phi 1 minus tan phi 2. Okay. And this is called as multiplying factor MEP. So you can calculate that multiplying factor, that is tan phi 1 minus tan phi 2, by using that calculation, cos inverse calculation. Otherwise, you can also use this table, power factor correction table it is. Okay, so this is called as a power factor correction table. In this power factor correction table, see here we are having initial power factor, final power factor. So initial power factor. Okay, initial power factor, say like from 0.6 onwards it is given. See, the values will be same, like you'll be getting different, looking like different power factor correction tables from, like in internet, I am just searching for power factor correction table. See, like we are getting, see, this table is having values from 0.6 onwards, right? Another one is having different range. But the values for same points will be the same. Values inside will be the same. The ranges only are different, right? Say like for this one, it is starting from 0.6 onwards, right? 0.6. And final power factor starting from 0.8 onwards. Okay, but here, another table which is available on internet. See, like, it is difficult to see, right? See, it is starting from 0.01 like that, right? 0.01 itself it is starting. 0.26. So more values are available. And like 0.76, 0.77 like that. 0.01 difference is in between the values. Okay, so it is having wide range, right? See, this is the entire table. It is having more range, right? It is starting from 0.01 itself. So the range can be different. Range can be different, but the values inside, for example, see, like here we are having 0.6. If I'm taking a value, my initial power factor, initial cos phi or power factor is 0.6. Final power factor is 0.95. My value is 1.005. Okay, if I'm checking here, 0.6, 0.6, 0.95, same value I'm getting, 1.005. Okay. So like that, different tables will be available on the internet, but that values will be the same. Ranges only will be different. Okay, that ranges only will be different. Okay. So anyway, this table is enough. I have just attached that with the PDF. Okay, this one. Okay. So like we are having, like I have told you, I'm having an initial power factor. Power factor 1 is 0.6. And a final power factor 0.95. So how much is my multiplying factor or tan phi 1 minus tan phi 2? 0.6 initial power factor. Look through this first column, then go through this first row, final power factor 0.95. 1.005. This is our multiplying factor. Okay, 1.005 multiplying factor. So we need to calculate that load in kilowatt into multiplying factor 1.005. Okay, so that is how we are selecting the reactive power. So the reactive power, based on the reactive power to be compensated, we are selecting the capacitor. So like actually, you know, the capacitance unit is farads, already I have told you. Like if you want to convert that into farads, just multiply kVAR into 10 raised to 3 as it is kilo values, kVAR into 10 raised to 3 divided by 2 pi f V square. I will be rewriting this equation. Load in or reactive power in kVAR into 10 raised to 3 as it is in kilo values. I am just multiplying with 10 raised to 3 divided by 2 pi FV square. You will be getting the capacitance in farads. But it is not required while doing the projects, like we need that kVAR value only. Okay. Okay, so here is an example. A three-phase motor of 50 kilowatt is having power factor of 0.61, which has to be improved to a power factor of 0.96. Determine the size of capacitor. How to size the capacitor? Actual power factor is given as 0.61. That is the current power factor. Target power factor cos phi 2 0.96. So we need to calculate tan phi 1 minus tan phi 2, 0.61 and 0.96. Let us go to the table. 0.61. 0.96. Meeting point 1.006. You may also try the calculation. Both values will be the same. So that we are multiplying that with the connected load, right? Load in kilowatt, 50 kilowatt into 1.007. So we are getting 50.35. Okay. In this case, it is close to that active power, 50 kilowatt. In all cases, it will not be the same. It will be depending on the value that we are selecting, like actual power factor and target power factor. Okay. Yes. Okay. Now, like This is a three-phase motor, a single load only. For that, we need a reactive or a capacitor with a rating of 50.35 kVA. Then suppose like for induction motor, like having various ratings, we are having a table like this. For selecting the capacitor rating, for induction motors, we are having a table like this. Capacitor rating for direct connection to induction motors in kVA. So based on the motor rating in HP and the motor speed in RPM, let us select the capacitor rating from this table. Okay, so for example, for a motor rating 3 HP with 3000 RPM, I need 1 kVAR of capacitor. For a motor rating 30 HP, 1000 RPM speed, I need 10 kVAR of capacitor. It is only for induction motors. Capacitor rating for direct connection to induction motors in kVAR. But any type of inductive loads, the capacitor rating can be calculated using this equation. Load in kilowatt into tan phi 1 minus tan phi 2. Okay. So like that is for the case of individual compensation, right? Then I have told you about capacitor bank calculation. Capacitor bank calculation. Okay. So where to connect this capacitor bank? Location of capacitor bank can be at the bus bar of a main distribution switchboard or at the terminals of a heavily loaded feeder cable, right? I will show you a capacitor bank is connected. Say like in our previous project. The project that we have discussed in the previous class, like its transformer selection, right? That we have discussed. Here we are having that single line diagram. Single line diagram, right? Okay. So for the single line diagram, there you can find out it is MDB1. MDB1, location LV room, low voltage room. Total connected load is given here. Demand factor is given here. Maximum demand 160.24 kilowatt. Okay. From this is MDB or LV panel. From this MDB, different connection for SMDB first floor, SMDB second floor, third floor, then a DB final DB for the ground floor. Then you can see a 50 kVAR capacitor bank panel is used here. 50 kVAR capacitor bank panel. Okay. So there you can see it's a multi-step automatic switching capacitor bank with reactive power regulator. Okay, like APFC panel, right? APFC panel. So an APFC panel will be looking like this. APFC. Okay, it's an APFC panel. So what are the components inside an APFC panel? For an APFC panel, capacitors will be there, right? Capacitors will be there. Conductors will be there. Circuit breakers are there. APFC relay is there. That are the components inside an APFC panel. Capacitors, various size of capacitors are there. Conductors are there. Then circuit breakers are there. An APFC relay is there. A relay, you know, relay is an electrical component which is used inside the electrical system. It is used to check the abnormalities inside the electrical circuits. So we are having different types of relays. A relay is also a switchgear which is used to control, right? So relay is a control element actually. So relay, overcurrent relay, under voltage relay, then earth fault relay is there, directional relay, impedance relay, like that a number of different types of relays are there. Here we are using an APFC relay. APFC relay. APFC relay. So like on an APFC panel, like if you are going for an APFC panel, You can see that externally that power factor will be showing here. Power factor will be showing here. Inside that, the connection of the relay is coming, right? Okay, so that connection of the relay is coming internally. So there you can see like there is an APFC panel. So you will be seeing the power factor here at the display. At the back side, from inside the APFC panel, that relay will be connected. Okay, so it is a display of that APFC relay. So from here, you will be finding out that power factor. It will be displayed from the APFC relay. Its display. Power factor can be seen. Okay, this one. It's an APFC relay. So its display will be externally. So we can see that externally, that power factor. Other things will be inside. It will be connected to inside that APFC panel. Okay. So if we are going to the APFC panel, like this circuit connection of the APFC panel like this, there you can see these are capacitors, okay, then contactors, then circuit breakers. It is a main circuit breaker, MCCB, a molded case circuit breaker is used for the main protection. 3 phases are being connected here. Okay, MCCB. So it's a 3-pole MCCB, right? Then like here you can see 3-pole MCBs are used or MCCB based on the rating. Okay. Then here is a relay control, APFC relay control. Okay. What is this? These are contactors. Contactors are the switching devices which are used for high current switching such as capacitor switching, motor switching, etc. Okay. So you can see from here connections are going to the contactors. That is from this relay, APFC relay, connections are going to the contactors. This APFC relay needs current and voltage input. There you can see a CT, current transformer is there. It is used to measure the current. Okay, converting the current to a smaller value which is measurable by the relay. So by identifying the current and voltage, it can measure power factor. That power factor will be displayed here. So as per the power factor or as per the reactive power required, it can operate. See, it is connected with the contactors. So now it is finding out we need only, for example, see, I will be telling you by using some numbers. Suppose each of this capacitor is having 40 kVAR. Okay, 40 kVAR capacity. Totally, it is having 120 kVAR capacity. Currently, I need only 80 kVAR of reactive power in my system. So it can identify that, right? So it will be calculating and this relay will be operating only 2 capacitors so that it will be getting a resultant of 80 kVAR. Okay, so it's a multi-step capacitor bank. So the reactive power can be increased in steps. Capacitors, multiple capacitors are used here. So in steps of 40 kVAR, that can be 20 or something, right? Different values can be used. Here in steps of 40, we can increase the reactive power amount. If I need 120 kVAR, then it will be operating all these capacitors. So based on the requirement, by sensing that, it will be controlling the reactive power supply by operating the contactor. These contactors are switching the capacitor. If I need 40 kVAR only, then the first capacitor only will be switched on by the contactor through this relay, right? If I need 80 kVAR, both of them will be operated. If I need 120 kVAR, then 3 of them will be operated. Okay, so that's an APFC panel. So mainly it is having a main protective device, then circuit breakers, individual circuit breakers, contactors, capacitors, then APFC relay control. Okay.